So in section 13.4, we're going to look at independent and dependent events. An independent event is when we're looking at two different events and the probability of one event remains the same regardless of how the other event turns out. So the results or outcomes of one event are not going to have any effect on the second event. So independent events are two events where they're not going to have effect on one another. Dependent events are the opposite. So dependent events is the probability of one of the events is going to have an effect on the probability of the other event. So in this practice problem here, we're going to make a slight little change here so that it comes out crystal clear. I want to change this sum of 2 to a sum of 4. So if we go ahead and look at this example, we have 3 different events we're looking at. We have event A, which is going to be rolling a 4 on the red die. Event B is rolling a 1 on the green die. And then C is the sum of the 2 dice is going to equal 4. We want to determine whether each pair of events is independent or dependent. So for this first one here, we're looking at events A and B. So event A is my red die, I roll a 4. Event B is my green die, I roll a 1. I'm rolling 2 separate die. What I roll on the red die does not affect what I roll on the green die. So because of that, I would classify A and B, events A and B are independent. What I get on one die isn't going to affect the outcome or the probability on my other. Now let's take a look at events B and C. So events B and C, I'm looking at B was rolling a 1 on the green die, and event C is rolling a sum of 4 on 2 die. So if I roll a 1 on my green die, that's going to limit the number of solutions or number of possibilities I have when I roll my second die. In order to get a sum of 4, I'm going to be limited. I'm going to need to roll a 3 in order to make that happen. So because event B is going to have an impact on event C, these two events would be classified as dependent. Let's look at another example. So here we're looking at a fair coin is tossed twice. A is heads on the first toss, B is heads on the second toss, and C is heads on both tosses. So if I look at the pair of events, I'm going to take a look at A and B. So on my first toss I got heads, that's a 50% chance. B, my second toss, is a totally separate toss, I got a 50% chance. So what I toss on the first toss isn't going to affect what I toss on my second. So we would classify these as independent. Now let's take a look at A and C. A says I have heads on the first toss, and C says heads on both tosses. So if I have a heads on the first toss, I'm putting it together. When I do heads on both tosses, I'm going to be really looking at both tosses together. So I'm going to be looking at a combined sample space now, where I'm putting the two events together. So getting a heads on the first toss is going to affect the probability of getting heads on both tosses. So this here would be classified as dependent. What I get on the first toss is going to have an effect on the probability of the combined tosses. If I look at B and C, so B and C, I got a heads on the second toss and then a heads on both tosses. Again, for the exact same reasoning, because C is looking at the combined tosses, it's going to have an effect. My second toss will have an effect on that combined. So we would say that that is a dependent event. All right, let's look at one more example. In this example, we have a bag of marbles, and a marble is pulled out of the bag, and then it's replaced. A second marble is pulled from the bag. Are the two events independent or dependent. So let's say we had 10 marbles in the bag, and I pulled out one. So the one that I pulled out, could be a particular color or whatever, is 1 out of 10. When I put that marble back into the bag, I still have 10 marbles in the bag, and the probability of randomly pulling out another marble will be 1 out of 10. So 10 marbles and putting it back in the bag isn't going to change the probability of the second event because I'm putting it back or replacing it. So when we have situations where we're taking something out and then replacing it, it's not going to have an effect on the second event's probability. So two events that have replacement in it are going to be considered independent events. So this is independent. And I think we'll do a practice example of that on the next slide. All right, so the formula for independent events, so if we know that our two events are independent, the probability of A and B happening would be the product, the probability of A times the probability of B. So let's look at an example here. What's the probability of getting a 3 on the first toss, followed by an odd number on the second toss? So because we're looking at two separate tosses, the probability of getting a 3 on the first toss has no effect on getting an odd on my second toss. So because these events are independent, I'm going to use the formula up here. The probability of getting a 3 on the first toss and an odd on the second toss is going to be the probability of 3 times the probability of an odd. And if I think about my die, to get a 3 on my die is a 1 out of 6 probability. And to get an odd, if I look at my odds, I have 1, 3, and 5. So I have a 3 out of 6 chance of getting an odd. So the probability on my first toss of getting a 3 and on my second toss getting an odd is going to be 3 out of 36. To show that's true, we're going to use the rectangular area model to show the probabilities here. And so if I look here, in red is going to be my first toss, and that's going to be the probability of getting a 3 on my first toss. So I'm going to shade in. This would be my first toss is a 3, right? And then the probability of my second toss, I'm going to be looking at the outcomes where I'm going to get an odd on my second toss. So here I have odds on my second toss. Here I have odds on my second toss. Here are odds on my second toss. And then what I'm looking for is, where do I have both? Where do I roll a 3 on my first toss and get an odd on my second toss? And I can see that that's happening in 1, 2, 3 different situations. 1, 2, 3. So my probability of that event is 3 out of 36. So we can see that this is true by looking at the formula and using our formula, which is what we did here, and we got that 3 out of 36. Or we can draw a visual and look at it visually to determine that, yeah, I am going to get 3 out of 36 as my probability for that. All right, let's look at another situation here. Here we have Juan spins a spinner, shown below. He notes the area on which the arrow stops, and then spins a second time. Find the probability that the outcome of the two spins is both reds. Okay, so first we need to figure out the probabilities in this particular picture here. And so we know that the white is taking up a quarter of the circle space, the blue is taking up a quarter of the circle space, and that the red is taking up half of the circle's area. So because the events are independent, we're looking at just two separate spins. If we look at red both times, the probability of red on the first spin is a half, the probability of red on the second spin is a half. So that would give us a probability of 1/4 for both spins. If we look at the probability of white on the first spin, I can see that the probability of white is 1/4, and the probability of blue is 1/4. So the probability of white first, then blue second, would be 1/16. If I look at the probability of white first, that was a 1/4. If I look at the probability of red, I can see that red is a 1/2. So the probability of white first, red second, is going to be that product, which is 1/8. D, the last one here says not blue both times. So if the probability of blue is a 1/4, the probability of not blue is going to be 3/4. And we want both spins to be not blue. So 3/4 times 3/4, which is going to give me a probability of 9/16. Okay, so we looked at calculating independent events, and now we're going to take a look at how to calculate probabilities for dependent events. And the way that we're going to do this is we're just going to kind of think through it logically first. So here I have a bag of marbles. My marbles contain 10 red marbles and 8 blue marbles. So I have a total of 18 marbles. If I select a marble at random and then select a second marble without replacing it, what's the probability of selecting a red then a blue? Okay, so what we're going to do first is we're going to figure out what's the probability of selecting a red. So I can see that I have 10 red marbles out of 8 blue marbles. So I'm going to say that it's going to be 10/18. And then after I take out that red marble, now I'm down to a total of 17 marbles as a total, and I'm missing one of the reds. So I only have now 9 reds once I take that out because I'm not replacing it. So the probability of pulling out a blue on my next pull will be, I still have 8 blues, but it's going to be 8 out of 17 marbles. So the probability of selecting a red then a blue is going to be 10/18 times 8/17. And that'll end up giving us 80 over 306, which is 0.26 or a 26% chance of pulling out a red then a blue marble. So what I want you to notice here is that once we calculated that probability of the red and not replacing it, it had an effect. It changed the probability. It changed the number in our sample space for the second pool. So because the probability of pulling out a red had an effect on the probability of pulling out a blue, it's a dependent event. Anytime we have an event that has without replacement, that we're not going to be replacing the item that we're pulling out, without replacement is going to indicate to us that we're dealing with a dependent event. All right, let's take a look at a second example. So here we have a sock drawer, a drawer full of socks. You can see in the image here we have a messy sock drawer. And you have 10 pairs of white socks and 8 pairs of black socks. If you select one sock, then another sock without replacement, what's the probability you pulled out 2 white socks? So we have 10 pairs of white socks, which means that we really have 20, which means that we really have 10 pairs of white socks. We have 20 white socks, right? And 8 pairs of black socks, which means we really have 16 black socks. So if you select one sock, then another without replacement, what's the probability to pull out 2 whites? So we want the probability of a white and then times the probability of a white after we made that pull. So the probability of a white is going to be 20 out of 36 options. And then once I pull that white out, I'm going to be missing a white now, so I'm only going to have 19 whites to choose from and 35 socks left in the drawer. So to calculate the probability of pulling out both whites, I'm going to take 20 times 19 and multiply it times 36 times 35. And that gives us 380 over 1260, which is going to tell us that the probability of pulling out 2 white socks is approximately 30%. So what we did in both cases, and notice that again that both of those cases were without replacement, so we knew it was dependent. What we did to figure out our probability of the 2 events happening is we took the probability of the first event and then we multiplied it times the probability of the second event after we took care of the effect that the first event had on it. So the probability of A with the socks was 20 out of 36. The probability of A was 20 out of 36. And then once we had taken care of A, so B given A had taken place, the probability of B was affected and we adjusted 19 out of 35. So this here is the rule of probabilities. We'll use this rule whenever we have dependent events. We can actually use it for independent events. The only thing is that B, that we don't have to worry about given A. It would just be the probability of A times the probability of B because A didn't have an effect on it. So this is the one we'll use for dependent. And just remembering whenever we have a dependent situation of events, we want to make sure we're adjusting for that second probability. So after viewing this, you can go to Nearpod and try a couple of the practice problems we have there.